All right, here we go. So welcome to our second momentum video. So today we're going to learn about what's called conservation of momentum. All right, so this is very similar conceptually to the idea of conservation of energy. And fortunately, I think quite a bit easier. All right. Learning targets are here on the screen. Read them, learn them. Here we go. All right. So the law of conservation of momentum is here at the top. Law of conservation of momentum says, in the absence of external forces, the total momentum of a system will always remain constant. All right, so before we get too far into this, let me kind of explain what this is all about. All right, so a system is basically just a collection of objects in a problem. Okay, so for us, we're going to have one car driving along and colliding with another car. So our system will be the two cars. Or maybe it's two penguins standing in a frozen pond, and one of the penguins pushes the other one. So there, your collection of objects would be the two penguins. All right. An external force is a force that comes by an object that is not in the system. All right. So if in that example, a polar bear comes along and pushes the two penguins, if the polar bear is not part of our system, then the polar bear is an external force. Okay. We could, though, if we wanted to define our system to include the polar bear. It just sort of depends on your setup. Okay? And basically, we'll be talking about two different types of problems. Here we'll be talking about collisions. We'll be talking about collisions in which two or more objects are already moving and they run into each other. And what's called an explosion, in which two or more objects are initially in contact and they force each other apart. Okay? So, conservation of momentum. Here's what conservation of momentum does. It says that as long as there's no external forces, the total momentum of the system is going to remain constant. It's a direct result of Newton's third law, all right? And you should know that. So this results from Newton's third law, a little shorthand there, all right? So here's two objects. Here's object A, here's object B, okay? And they interact in some fashion, okay? Maybe they're moving along and they bump into each other. Maybe they're next to each other and they push off of each other. But the idea is anytime they come into contact, they're going to exert forces on each other, right? So your action force might be the force of object A pushing object B, and your reaction force might be the force of object B pushing object A. Well, if there are no external forces, these are our only forces, right? So the idea is these two forces are equal, right, by Newton's third law, right, action-reaction force. So let's just call those two forces F. Okay, they're equal, right? The only difference is one of them's to the right, one of them's to the left. So let's look at the change in momentum for each of the two objects. Well, the change in momentum over here is going to be, here, let me write this differently. So the change in momentum for object A is going to be negative F, right, however much force F is, times the time that object B is pushing it, right? And similarly, my change in momentum for object B is going to be F times that same amount of time, right? The two objects have to be in contact for the same amount of time. Okay, we talked about this when we did impulse. Okay. Oh, and look, so they're equal. So that means that the change in momentum for object A is equal, but opposite to the change in momentum for object B. All right. In English, all this means is any momentum that A loses, B gains, or vice versa. All right. So this means that the momentum of A final minus the momentum of A initial is equal to the momentum of A, Now this one, we get a negative sign here, right? So I'm going to switch it around and write it as initial minus final. Okay? And then doing a little bit of algebra gives us this. It shows if we add the initials to one side and the finals to the other, you get the momentum of A initial plus the momentum of plus the momentum of B initial has got to equal the momentum of A final plus the momentum of B final. In other words, the total momentum before the collision equals the total momentum after the collision. All right? So, the law of conservation of energy in equation form can be written two ways. This is the way you'll usually see it. The total momentum before the two objects interact is equal to the total momentum after the two objects interact. Alternatively, sometimes you'll see it written this way, and this basically just says any momentum lost by one object must be gained by the other. So their changes in momentum are equal and opposite. Their impulses are equal and opposite. Okay? So that's a whole bunch of algebra. most of our problem solving is going to stem from this right here. Okay? So let's do a problem. All right? So here we go. Example number 1. 1,200 kilogram truck is rolling at 5 meters a second, blah, 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 blah. You can read it. Okay, so make a drawing. Draw arrows to represent your velocity. Okay, so here's my truck. Truck. Mass of truck. Notice I'm going to use subscripts to indicate which object is which. All right, it's rolling at 5 meters a second, so the velocity of the truck is 5 meters a second. When it collides head-on with a 500 kilogram car. So here's my car. I didn't make my vehicles happy, I'm sorry. Gotta stop rushing. I miss these smiley faces, they're so important. Alright, so our car is 500 kilograms and it's rolling at 8 meters a second. Since it is a head-on collision, it's got to be going the other way, right? That's what we mean by head-on collision, okay? Now, they're going to collide, which means these velocities are going to change. So these are both initial velocities, right? Okay? Now, I'm going to leave a little bit of space here to do some work. So I'm going to skip down a little bit. And then it says immediately after the collision, the car is going backwards at 3 meters a second. Well, on my drawing, to the left is forward, right? The car is driving forward. It's a head-on collision. So after the collision, the velocity of the car final, it's going now backwards at 3 meters a second. And the question is, what is the velocity of the truck after the collision? Okay? Now, before we go too far, I should point out you need to come up with a sign convention. I'm going to stick with our standard, right is positive, left is negative. Okay? So this is weird. What this means is if you didn't make a drawing, you might have read this and thought, oh, the car bounces back and made this final velocity for the car negative. But it's actually positive, isn't it? Because it's going to the right, okay? The only velocity that's negative is the initial velocity of the car, because even it's driving, quote unquote, forward, it's moving to the left, right? And this guy's positive, and this other one we don't know. All right, so written in black right now is everything we know. All right, so the idea is each of these velocities corresponds to a momentum, right? Remember, momentum is mass times velocity, okay? So all I'm going to do is I'm going to, for each velocity, I'm going to find the corresponding momentum. So here's the velocity of the truck initially. That'll allow me to find the momentum of the truck initially. So just mass times velocity. So 1,200 times 5 gives us 6,000 kilogram meters a second, okay? Oops. All right. For the car, this one, the momentum of the car initially is 500 times negative 8, or negative 4,000 kilogram meters a second. Okay? Down here, after the collision, the momentum of the car after the collision is mass times velocity, so 500 times 3 is what, 1,500 kilogram meters a second. Okay? But I can't find this guy because I don't know the velocity. All right? Now, what I do know, though, is this. I know my total momentum has to be the same before and after. So let's find the total momentum before the collision. Oh, well, that's just 6,000 minus 4,000. So you get 2,000 kilogram meters a second, right? Total momentum before the collision. Let's see, we had 6,000 from the truck, negative 4,000 from the car. Add them up, you get 2,000, right? Okay. Oh, well, that means my total momentum after the collision has also got to be 2,000 kilogram meters a second, right? And so that represents the sum of this and this. So that means that, let's see, if the car's final momentum is 1,500, 1,500, but the total is 2,000, that means we must have another 500 here, right? So that 500 plus 1,500 gives us our 2,000. Okay? Oh, and now I can find my velocity, right? Because if P equals mv, I know the final momentum of my truck, I know the mass of the truck, so I can find the velocity, right? So it's basically just going to be v equals momentum over mass. So here's my momentum, here's my mass, so 500 over 1,200 gives you 0.41 meters a second. Okay, I guess it's 0.416 repeating. Let's just call it 0.417 meters a second. Okay, and there you go, and there's the answer. Okay, so conceptually, that's how all of these problems are solved. But that was a lot to keep track of, wasn't it? And I'm guessing maybe some of you I lost. And if you're in that boat, I want you to pause the video right now, or not pause it, rewind the video, watch that again, okay, and see if you can figure out what all the numbers are, because it's important, all right? And again, the main thing that this all stems from is this idea that the total momentum before the two vehicles collide is equal to the total momentum after they collide, okay? So this is kind of like when we did energy, how we said that the total energy at one point is equal to the total energy at another point, right? Okay. So, but this is a lot to keep track of, all right? So, there's an, oh, actually, real quick, before we do this, there's an easy way to do this. Before we do, I want to point out one other quick thing, okay? So, let me do this. Yeah, all right. Let me also do this. You know, it'll come up in the homework. It'll come up in the homework. I'm going to not worry about it right now. Here's what I was going to do. You can find the change in momentum for each of the vehicles, and what you discover is that the truck, its momentum went from 6,000 down to 500. So it lost, what, 5,500 units of momentum? And in exchange, the car gained that same amount. The car's momentum went from negative 4,000 up to 1,500. So the change in momentum for both vehicles is 1,500. The only difference is the change in momentum for the truck is negative. Change in momentum for the car is positive. All right, there you go. A lot of numbers. Wow. So here's another way to do this. All right. So again, you always want to start with the drawing because it'll help you keep track of your signs. All right. So I'm going to plow through those the drawing again real fast. So here's my truck. The mass of the truck is 1,200 kilograms. The velocity of the truck initially was, what, 5 meters a second this way, so it's positive. The question wants us to find the final velocity of the truck. Here's the car. Mass of the car is 500 kilograms. Velocity of the car initially is negative 8 meters a second. Velocity of the car final is 3 meters a second. Okay? So, here's the other way of doing it. And it amounts to the same thing, but it basically is one big step. All right? Remember, the whole premise behind this is this. The total momentum before the collision is equal to the total momentum after the collision. Okay? So what that means for us is that the momentum of the truck before the collision plus the momentum of the car before the collision has to equal the momentum of the car after the collision plus the momentum. Oops, sorry, switch to those. Let me write that the other way. It's got to equal the momentum of the truck after the collision plus the momentum of the car after the collision. In other words, all the initials added up equal all the finals added up. Okay? And then I'm just going to replace each of these P's with an MV. Okay, right? Momentum is mass times velocity. So this is mass of the truck times the velocity of the truck initially plus the mass of the car times the velocity of the car initially equals the mass of the truck times the velocity of the truck final plus the mass of the car times the velocity of the car final. Okay? So notice there are 6 variables here. There are 2 masses, car and truck, and 4 velocities, 2 initials, 2 finals. Okay? Every problem is going to give you basically 5 of the 6, and you're going to solve for the missing one. All right, so let's plug our numbers in. You get 1,200 for the mass of the truck times its initial velocity, which is 5, plus the mass of the car, which is 500, times the velocity of the car initially, which is 8, equals the mass of the truck, which is again 1,200, times the thing we're looking for, velocity of the truck final, plus the mass of the car times the final velocity of the car. Okay? And this is literally the exact same thing we just did, except we're doing it in one big long equation. Okay? So 1,200 times 5 is 6,000 kilogram meters a second. Oh, I forgot a negative sign, didn't I? I'll do it here in green so it stands out. This was supposed to be negative velocity. I forgot to put it here. Okay? So that means that this is minus 4,000 equals 1,200 times VTF plus 1,500 This gives you 2,000. This is our total momentum before the collision, equals our momentum after the collision. Subtract the 1,500 and you get 500 equals 1,200 VTF. Divide and you get the same thing we got before. Okay? So the biggest thing with solving these problems is going to be making a drawing, watching your signs, writing out your givens. Okay? That honestly is all there is to this chapter. Almost every problem is just like this. Okay? All right, so a couple, I guess, minor variations. So first of all, let's take a look at the energy in the system. Okay? So here is what we know. Let me do this. Well, I guess, shoot, we'll go through and just write out everything again. All right, one last time, we got to do this. All right, so here was the truck. The mass of the truck was 1,200 kilograms. The velocity of the truck initially was 5 meters a second. Velocity of the truck final was 0.416 meters a second. That's what we found. Here's the car. Mass of the car, 500 kilograms. Velocity of the car initially was negative 8 meters a second. Velocity of the car final was positive 3 meters a second. Okay? So, all I'm going to do now is take a look at the kinetic energy. Okay? So, the velocity of the truck initially gives me the kinetic energy of the truck initially, right? So I'm literally just doing 1/2 mv squared. Okay? So I'm going to do this 4 times, once for each of these 4 velocities. Fortunately, you won't have to do this too often, all right? Basically, these are going to result in yes or no questions, which you will see. Now, if I can find in my notes where I actually found these. I apologize. There it is. Sorry about that. Okay, so if you do half of mass times velocity squared for the truck, with this initial velocity of 5, you get a total kinetic energy initially of 15,000 joules for the truck, and the kinetic energy of the car initially, similar by doing half your mass times your velocity squared, that gives you 16,000 joules, which means that our total kinetic energy before this collision is what, 31,000 joules, right? All right. Now, if we repeat this process for after the collision, the kinetic energy after the collision for each object, so for the truck after the collision, if you do half of mass times this velocity squared, it gives you 104 joules. And the kinetic energy of the car after the collision, just doing 1/2 mv squared, gives you 2250 joules. And so the total kinetic energy after the collision, when you add these together, it gives you what? 2,354 joules. So look at this. During this collision, we lost a ton of energy, didn't we? Before the collision, we had 31,000 joules of energy. And after the collision, we only had like 2,000 joules, right? All right. And so it turns out most of that energy is lost to heat. In the case of cars, a lot of the energy goes into deforming the material, right? The cars get all banged up, right? So you do lose energy, all right? But despite that loss of energy, you will not lose momentum, all right? So in any collision in the world, assuming no external forces, your momentum will be conserved, your kinetic energy may or may not be conserved, depending on the makeup of the objects, all right? Which brings us to this. There are 3 different types of collisions, all right? The one we just looked at is what's called an inelastic collision, all right? This is a collision in which the objects don't stick together, but some kinetic energy is lost, all right? Now, if we had figured out those kinetic energies, and we'd found that this kinetic energy did, in fact, equal this kinetic energy, then that would be what is called an elastic collision, all right? An elastic collision is a collision in which the objects don't stick together and all the energy is conserved, okay? Finally, it is possible for the objects to stick together, and in that case, this is what's called a completely inelastic collision. It's a collision where the objects stick together, so they can have the same final velocity. And it turns out that this is the most kinetic energy you can lose, is in the case of an inelastic collision. Okay? So let's do one of those examples. This is the last one, and then we're done. All right, so we're going to start with the same given information. So we're back to the stupid car and truck. So here's the truck. Mass of the truck is still 1,200 kilograms. Velocity of the truck initially is still 5 meters a second. Here's our car. Mass of the car is 500 kilograms. Velocity of the car initially is negative 8 meters a second. All right, but so what happens is they're going to stick together. Okay? So the reason this is important is what it means is that if they're stuck together, that means they're moving with the same final velocity, right? So that means the final velocity of the truck and the final velocity of the car are equal. So we don't even need to distinguish between them. So we're just going to call the final velocity of the two objects stuck together VF. Okay? And solve it. All right? And I'm going to solve it using the one equation, right? Our total momentum before the collision has got to equal our total momentum after the collision. So that means the momentum of the car initially plus the momentum of the truck initially. So it's a mass of truck times velocity of truck initially. That's the truck. Plus the mass of the car, velocity of the car initially, that's the car, equals the mass of the truck, velocity of truck final, plus mass of car, velocity of car final. Okay? And just plug in your numbers. So let's see what we get. We're going to get not enough room for one thing. So you're going to get 1,200 for the truck times its initial velocity of 5, plus 500 times its initial velocity of negative 8, equals the mass of the truck, which is 1,200, times its final velocity, which is what we're looking for, VF, plus the car, 500, times its final velocity, also VF. Okay? So, here's what we've got. We're almost done here. So this side of the equation just gives us 6,000 minus 4,000, so you get 2,000 kilogram meters a second, equals, on this side of the equation, you've got 1,200 VF plus 500 VF, that's 1,700 VF. So divide both sides, and your VF turns out to be 1.17 meters a second. Okay? And just quickly by inspection, you can see both objects lost velocity, so we lost kinetic energy, right? And you couldn't possibly lose any more energy than this. All right? So there we go. So most of the problems are going to be this. You'll be given, some initial information about the objects, and you'll be asked to find the final velocity. And then a lot of them will just say, what type of collision is it? Is it elastic, inelastic, or completely inelastic? And if it asks that, you got to figure out what happened with your kinetic energy. That's kind of the deal. All right. So there we go. Happy momentuming. It's not a word.